Okay, so this is the video. Homework 2, Module 6, electromagnetism. Topic is on the motor effect. Okay, let's get into the multiple choice. So the first question lists out a straight wire that is carrying a current and is placed into a magnetic field, shown in the picture below. What is the direction of the force on the wire? Okay, so remember that the perpendicular components of the current, yeah, and with the magnetic field, uh, is the source of the force. So the perpendicular component, that will be this directional current. So if you use your right hand rule, you will see the force is actually out of the page, right? And yeah. So question 2, when a straight wire carrying a current of 16 amps and placing a field like this, what is the magnitude, right? Again, so this is you can just use the motor effect equation. So F is equals to B times I times L, sine of the angle in between. Okay, and this angle is 45 degrees. Okay, be aware that this um, the 5 centimeters here is actually the perpendicular component. So this 5 centimeter here is actually L times sine of the theta. So you do not actually, so if you use the 5 centimeter, you don't need to calculate any, you don't need to multiply by the sine of the angle anymore. Yeah. And so just be aware of that. And question 3, a fixed conductor is placing closely over a disk magnet that is floating on top of the water. Okay, so when the switch is closed, the magnet moves to the right. Okay, so when the switch is closed, it's going to be a current. Uh, right. So which of the following rows of the table correctly identifies the direction of the current and the magnetic field? Okay, so the magnetic field and the current must make sense in terms of right-hand rule. So let's have a look at selection A. So say if that the current direction goes from X to Y, yeah, and in that case, the magnet actually moves to the right. Because the magnet has moved to the right, we can deduce that the magnet has experienced a rightward force. We could also deduce wire itself experience a leftward force due to Newton's third law. And using your right hand rule, if current goes from X to Y, and then use your right hand rule, you could determine that the the magnetic pole should have north pole facing the wire and away from the water. Okay, so selection A actually meets all the consistency, so A is the right choice. You can verify yourself for B, C, and D if you feel confused. Let me know. I'll explain it in class. Question 4. So a student performed an experiment trying to measure the force on a long current carrying conductor that is placed inside of an external magnetic field. The graph shows how the force on 1 meter length of the conductor varied as the current throughout the conductor varied. Okay, so you know how this is motor effect, and motor effect has this equation, and we are plotting against F and current, so B and L is our gradient. Okay, so from measuring the gradient of this straight line, you can calculate BL, and then divided by L, you can get your field. Yeah. Question 5. Two parallel wires, each carrying the same magnitude of current. Uh, Current is denoted as I, small I, flowing in the same direction and are placed side by side as shown. Point P is midway between two wires. The magnetic field strength at P. Okay, so if from the top wire, you know, a magnetic field is directed into the page at point P. However, for wire on the below, it has a magnetic field out of the page in the middle, and then they have the same strength because the distance are the same, same distance. In that way, the field just cancel out, so it's 0. Question 6, two parallel straight wire are placed blah, 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 and 14 centimeters long, and then the other one 30 centimeters long, carries a current of 2 and 3 respectively. Okay, so this question, you can just use the parallel conductors equation, right? F over L. Right, F over L, force unit length is equal to a constant, 2 pi, and so I1, I2 divided by the distance, okay? Well, in this case, so this force per unit length, be careful we're trying to calculate the force, so you want to multiply both sides with L, right, as in the length. The length that we should use is the shortest one, okay? It's the only force that's being experienced is due to the common length between the wires, right? This excess length does not contribute, okay? The common length. So 30 centimeter, do not use 40 centimeter, okay? And the force on conductor B, right? The current direction are the same. So you should use your two-hand rule and you should get attractive force, right? So B is going to experience a downward force. And that way we get A. That's our answer. Question 7. Question 7 is a straight conductor connected to AC power supply and suspended horizontally from a fixed point using a sensitive spring balance. Okay, so we have AC. AC is alternate current in the sense that the current goes back and forth, back and forth. Which statement correctly describes a force measured by the spring balance? It's going to oscillate, obviously. Okay, so say that, for instance, that the current is running to the left. Well, in this case, that's a force. If you use a right-hand rule, you can deduce a downward force is going to be experienced by the wire. Okay, so that the spring will be pushed downward. And another instance that when the current is going to the right, so the force upward will be experienced, so the spring will be pushed upward. Okay. So yeah, the force, because it's upward and downward fluctuating, we have like a sinusoidal force variation in the spring. Quite understandable. Okay. Question 8. Two long parallel current carrying conductors are placed at a distance r apart. Okay, so a force of magnitude r of magnitude F is present. If the current in each conductor is doubled and distance between them is increased to 2 times of the original, what would be the force between them? So we know that F over L is equals to a constant times by the current 1, current 2 over distance, okay? So, or like distance, I'll use R. If I double the currents, okay, I get multiplied by 4 on the top. If I double the bottom, I get multiplied by 2. They together becomes multiplication by 2. So it's 2F, okay? Continue on question 9. We have a metal loop labeled as XY, WXYZ is connected to a battery and is placed in a uniform magnetic field. The current flow through the loops is shown in this as a diagram. Which statement is correct? Okay, so A says that the magnitude of the force acting on XY and WX and XY will be equal. So XY here actually has no force because it's parallel to the field, right? Remember that the field goes from north to south, so it's actually parallel to the current. So there's no force on XY and WZ. So they're not equal, so this is wrong. Question B, selection B says that the net force acting on the metal loop will be 0. So it will not move. This is true for the first part. The net force is 0, but the torque isn't 0. It will still move by rotating, okay? In a sense that WX experience a force if you use your right hand rule. There should be a force downward, so a downward force here, and then if you use your right hand rule, there will be an upward force there, and they will just rotate in sort of this anti-clockwise way. So like D will be the right choice for this. Okay. And question 10. A wire is wound into 5 centimeter times 7 centimeter rectangle and is connected to a battery as shown. The wire is fixed to an insulated cylindrical axle so that it is free to rotate and place adjacent to the north pole of the magnet. Okay, so that's north. So the magnetic field sort of goes this way. This is the field strength, and the plane of the rectangular wire is parallel to the table. Okay, so it's pretty much just as shown here. So now when the battery is turned on, 3 amps of current flow through the wire. Okay, so this is my current, it's gonna run this way. You can determine that from the length of the terminals here. What is the magnitude of the torque on the wire resulted for that's due to the force from the magnetic field. Okay, so the wire here carries a current of this much, so the current actually goes this way. Okay, so if you use the right-hand rule, you can determine the direction, and you can calculate the torque as well. Like torque is given as R times F. Here, F you use the motor effect, so BIL, right? It's perpendicular, and this R is just 7 centimeter. This L is 5 centimeter. Okay, it's pretty straightforward. Continue on with external response. Question 11. This one's pretty involved. It's a comparison question, I think. We have two straight metal rod P and Q. They have the same length. They are placed in two different types of magnetic field, a field that's going out of the page, and then the field that's going directly upward, and they carry the same current. Okay? Compare the forces acting on the two rods P and Q throughout their circular motion. Yeah, they also like spins around. Okay, include a relevant equation and support your answer. So what I said is that I'll just read it. So in this context, the motor effect is very significant, right? Because we have supplied current and it's in a field, so they experience the motor effect. It states that, so definition, right? Make sure to write it down. It states that current carrying conductor experience a force in external magnetic field. That's my equation, and I sort of demonstrate what those symbols are. And then secondly, I split into dot points. All right, one dot point for each diagram, so that makes more sense. This is kind of like an introduction to dot points. All right, we use this method to answer external response for many questions now. Now, for conductor P, right, which is the diagram X, right? So the conductor rotates; it remains perpendicular to the magnetic field. Guys, whenever the question tells us to describe force, right? You always focus on two different aspects of the force. First of all, it's the magnitude, right? Does the magnitude change throughout like this process? The second of all is your direction. Okay, does the direction changes and how does it changes? Why does it changes? Okay, so this is like if the question wants to describe a force, this is what you do. Okay, direction and magnitude. How does it change and why does it change? Okay. So yeah, that's exactly what I said here. So I said the magnitude of the force stays fixed because it's always perpendicular, right? BIL, nothing changes in BIL. And the direction of this force must be always perpendicular to the current and the magnetic field. So as it rotates, the current switches, like it changes direction radially, as in like it goes through this radial directions. So if we use the right-hand rule, we can see how the magnetic field it's okay. It acts as a perpendicular direction towards your tangential velocity. So the tangential velocity goes like this, right? The force always like is in opposite direction. So if the wire was here, the tangential velocity would be this one, and then the force would be this one. Okay. So that's I'm trying to explain this. Okay. And then for the next dot point, you can sort of use the same strategy, right? Magnitude and direction. So for conductor Q, right? So in this case, as it rotates, it's no longer always perpendicular. Okay, so it varies from 90 degrees. That's going from here, which is 90 degrees, goes to 0, and then to 180, and then, goes to 0, and then again. Okay, it's just back and forth, right? So this is what I wrote down. So in terms of angle, right? Hence, the magnitude of the force varies periodically, okay, as you rotate. And I even draw a little diagrams, like it's just like a little cosine function. As it starts, it's maximum, and then reaches 0, and then another maximum, but in the opposite direction, right? So start maximum, 0, opposite direction maximum, 0, and back. Okay, you can draw little diagrams. Drawing diagrams really helps, okay, in physics, even if the question didn't ask for a diagram. Okay, so and I sort of just describe that, and then the direction of the force acts out of the page. Like just use your right hand rule. It's out of the page here, like for this semicircle, and it's into the page here. Okay. So yeah, just sort of explain, and then we're done for this question. Okay, so the introduction, defining motor effect, 2 dot points for two different cases, and you're trying to compare them, and then say the differences in magnitude and direction in terms of the force. Okay, you could also talk about similarities. So this question says compare, and people would also use similarity and differences. In a way that it is done correctly, I think if you do similarity and differences, you could also get marks for this question, as in a full mark. But I just think that this way is better to answer the question. Okay, so I didn't really use similarity and differences. Question 12. A straight conductor is made to levitate 0.5 Tesla magnetic field. In a magnetic field is 0.5 Tesla. The conductor has a mass of this much. It's a mass per unit length. Okay. You guys have to be able to get used to those like per unit something sort of physical quantity. We've encountered one, it's called force per unit length, and then we denote it with F over L. This is mass per unit length. It's kind of like a density, but like each meter you increase a little bit of mass, right? What is the smallest magnitude of the current needed for the conductor to levitate? Okay, so we're going to define that the mass density is lambda, take a vector, and right. So and then we use motor effect. We know how the net force in order for levitation, net force is zero. So BIL minus mg is zero. Okay, and then because m is equals to L times lambda, that's just by definition of what lambda is, right? We can get rid of the mass, and then we can cancel out L. Okay, and then we end up getting I is equals to lambda times G over B. I'm getting our final answer. Okay, 6.66 amperes. For the next question, we have a definition of amperes being used as question. Okay. Yeah. So the first question just state out what is the old definition. Okay, and demonstrate it's 1 ampere using some physical equation. So yeah, it's like I covered this in class. It's pretty trivial. So the old definition says that we have a specific arrangement between two parallel wires, in such that if the wires experience a force of 2 times 10 to the power -7, when they are separated exactly 1 meters apart, and then the wires are exactly 1 meters in length, the current in it is exactly 1 ampere. So that's defines what 1 ampere means, and then you could just use the parallel wire equation to calculate its 1 ampere, okay, from the given data. So then the new definition of ampere relies on our very accurate calculation of what electric charge is. Okay, and then we use it, and then we use more intrinsic understanding of current being charges moving through a point to define. Okay, so there's that. Question 14, we have 3 identical 10 centimeter long wire that are placed parallel on top of a table. XZ carries a current of 4 and 5 amperes respectively. The net force acting on wire Y due to X and Z is 0, so it is levitated or it is balanced. So the net force on Y is 0, as I labeled here, right? Yes, you could also label on the diagrams in the test to make it more obvious to you. I don't know, make it more like communicate your the marker, anything. Okay. A asks for what is the direction of the current passing through wire Z. Okay, so in order for wire Y to be balanced, we know how wire X and Y experience a attractive force. Okay, so Y is experiencing upward force because of this. Now, in order to balance that, you need Y to experience a downward force due to Z. Okay, so it has to be attraction due to Z and Y between as well. So in order for an attraction force, Z must have a current going to the right as well. Okay, so that's me just trying to explain that. And B, show that the magnitude of the force passing through Z is this much. So you can use the fact that the force on Y is balanced, and use your parallel wire equation, cancel out like terms, and then rearrange for IZ. Okay. Algebraically, it could be very challenging for students not used to do math in physics. But come on, it's just algebra. As soon as you get the physics right, so the physics here is just net force 0, and then use the equation. Rest of it just math, rearrange. Okay. And then part C, the current passing through wire Y is reduced to 1 ampere. How does this change to the force acting on wire Y? We know how the force per unit length is proportional to the current, right? So if it's reduced by a factor of 5, right, this will still produce a zero net force because the force from wire Y and Z also reduced by a factor of 5 because yeah, it's just proportional to IY, current Y. So the force will be still balanced. No change of like the state of motion. It will be all stationary, but um, the force will be reduced. Okay, the force will be smaller. It's still balanced, but the smaller force will be balanced. Okay, so sort of say that. Question 15. Question 15. Yeah, this one is quite challenging. So you have to understand what does it mean to be the apparent weight and then like the normal force and stuff. Being able to write free-body diagrams and rearrange equations to find the equation to plot the graph. It's all quite challenging. So the students perform an investigation to study an interaction between two parallel wires. The wires are copper rods. They are 1.5 meters long and they carry 75 amperes of current each. This is very crazy. Okay. It's a big current. Okay, 75 amperes of current. It was just made for this question. It's not that realistically possible because that will just literally melt the copper. Okay, the top rod is fixed to a stand while it's fixed to a stand, levitating above the bottom wire. So the bottom conductor rests on the insulating electric balance. So the distance between them can be varied, and that's our independent variable, I think, right? So we vary them. Okay, and the result is shown. So the result shows like a manipulated data. Like we would vary the distance between them, which is a small d right here, and then we would do it in different increments. But the data shows 1/d, so it's already been like sort of linearized for you guys, so you don't have to do it yourself. Right, so it's 1/d, okay, and it's ranging from 20 to 2.5, like this. So because it's 1/d, so as you go downward of the table, 1/d decreases, that means d actually increases. And the mass measured by the balance, which is the dependent variable, increases accordingly. Okay. All right. So question A: what is the direction of the current flowing through the bottom rod? We note how. Okay, so let me have a look. Uh, Okay, so the table indicates as our d increases, okay, the apparent weight increases. So because like if you increase your d, that means a smaller magnetic force if there is any magnetic force, right? So and then the magnetic force. Okay, so like a larger distance is a smaller magnetic force, but the mass increases. Okay, this indicates that the magnetic force must be pulling the bottom rod upward. Okay, so as the magnetic force gets weaker, this upward force gets weaker, and then you get a heavier sort of like weight. Does that make sense? Okay, so this tells you the fact that d increases, mass increases. It tells you the magnetic force is upward. Okay, I get it. It's kind of logically bit complicated, but it'll get through. So the table indicates that as d increases, the apparent weight increases. The magnetic force between the two parallel conductors are proportional to 1/d. So as d increases, force reduces. To have apparent weight increase, all right, so the magnitude of the force must be applied. Magnetic force must be applied upward. So when the upward force decrease, you're increasing downward force. Okay. So we in that case, we can deduce the current on the bottom rod is to the right, so that they experience attractive force to be pulled upward. If we pull the data, okay, so apparent mass is the y-axis, right? So apparent mass is the mass calculated from the normal force, which is the apparent weight. Okay, so know that. And then the x-axis should be 1/d straightforward. Okay. To figure out the theoretical relationship, we need to consider the fact that the bottom rod is balanced. Okay, and it is equals to 0 net force. Okay. So its net force, we have a component of normal, we have a component of the upward magnetic force, we have a component of the original or the actual weight force, which is m0 times g, I denote m0 as my initial mass, so like the mass measured without any magnetic field or current. Okay, so if you write that equation, n minus m0 times g plus fb is equal to 0. N here is our apparent weight. We can calculate apparent mass from n by expressing n equals to m times g. Okay, so if you rearrange this equation by moving m times g to the right hand side, and then expressing fb in terms of parallel force in the magnetic field, and in this case we can relate m as our dependent variable, and then 1 over d as our independent variable. Okay, these are all constants. Okay, this is my actual weight, it's constant. So yeah, this is me rearranging the equation for the line of best fit I'm gonna draw. Okay, so we have a y-intercept. Y-intercept is the original mass. We have a negative gradient. Okay, so as you plot the data points, it's expected to be a negative gradient, and we have a y-intercept somewhere. Okay. All right. So yeah, there it is. That's our graph. Okay, if you plot all the data, and then you can calculate the slope, right? So plot the data from the table with the line of best fit and all that. Question C says using the graph calculate the value of the magnetic permeability constant. So we're calculating mu. Okay, so knowing that our theoretical equation is right here, this will be our slope. Okay, so the slope will be that rearranged for mu naught to get your final answer. This question is a bit challenging, so if you didn't get this question first score, that's fine. Okay, watch this video if you understand it after this video, and you should try this question yourself again, maybe tomorrow, like a day after. All right, and then if you still feel confused, let me know in class. I'll explain in class, and then I'll make sure I understand why you're confused. In continuation, we have question 16. It's a conducting rod with a mass per unit length of 2.0 kilogram per meter. Again, I denote that with lambda. Is placed across two fixed rails in 0.25 Tesla magnetic field. The rails are placed on a horizontal surface and connected to a 25 volt power supply. The coefficient of friction between the rail and the blah 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 is 0.55. When the switch is closed, the rod starts to accelerate at 0.1 meters per second square, the rate of that. To the right, what is the total resistance of the circuit? Okay, seems like so many information were given and very difficult. It's actually very easy. What we're doing is we pretty much use a voltage to supply a current, and that current is dependent to the resistance due to Ohm's law. Okay, and this current induces a motor effect. The motor effect in the magnetic field produces a force, and that force results in a 0.1 meter per second square acceleration. We could use Newton's second law to equate with motor effect, right? And then we also know the mass length, so we can calculate something like in terms of the force. Okay, so and then we can calculate the total resistance from that. So this are all the equations you know. So we know that F equals ma, Newton's second law. This is equals to the magnetic force I apply to it, subtracted by the friction force. Okay, friction force is mu n is just mg. Okay, according to Ohm's law, I is equals to V over R. It's pretty trivial. So if you plug that in, right, so you get ma is equals to this big thing, right? And if I calculate for resistance, if I rearrange for R, right, you will get this relationship. And then you get L canceled out because you can substitute this mass with lambda times L. Okay, so I don't care about the length here, even though it's not given. Okay, it just cancels. Right, and then you just end up rearrange to this equation and then you substitute values to get the final resistance. Okay, this is all for the normal questions. And the challenging questions here is also discussed in the challenging material or in the extension material in the lesson booklet. If you had very strong skills in 4-unit calculus in terms of integration techniques, including just like basic integration techniques, you have to be very fluent to it. You are able to read the lesson booklet's extension material, which discusses non-parallel conductor. When we talk about parallel conductors, right? What if the wires are not parallel? If you have like a certain angle to it, there's still gonna be a force, but what is it? Like, how do I calculate that? Okay. the difficulty rises because in parallel wire, right? So every point on that wire is the same distance away from the other wire, which means the currents for each wire, they are in a magnetic field that is the same distance from the field from the other wire. All right, so they're gonna experience the same force. So it's just the same force everywhere. You just multiply. Okay, but in this case, each point on the top wire, which is this dashed line wire, is at a different distance, which we express as r as function of x. Because of this distance, the magnetic field strength, right, which if you recall, due to a wire on the bottom is B equals to mu 0 times by current divided by 2 times the distance in between. And that distance varies with like which point of the wire you're at. Okay. So if I define that as my x, I like to indicate a point on the top wire as my x variable, right? This will change. So the magnetic field is different at every point, and we need to sort of add up the contribution for each point on this wire. They experience the force, and then we need to consider sort of doing calculus. We need to use an integral to sum all that force together. Okay. So each distance corresponding to each magnetic force at each location of this x, right, which corresponding to like a charge that's moving to the right or something. Okay. Right, so this angle here, we denote this as phi, and then the total length is L or something, and then the initial separation is R0. Okay, you have to do some initial consideration here. Yeah, the derivation I won't go through, but the question A is pretty trivial. You probably could still answer this without reading the extension material. This question says that explain why the following equation to parallel conductors is not applicable in this case. So the above equation was derived using the assumption that B is the same for both conductors everywhere, which is not true in this case, okay? However, in this case, the magnetic field felt by the wire are different at different points along the wire. This would be stronger when the wire are closer and will be weaker when the wires are away. So you need to be able to formulate that exactly how strong, how weak. Question 17. So in the extension section, we actually formulated that. We actually summed all up, right? The QEB forces to get this, right? So we're now getting a force per unit length, right? Which is a function of location, like where about are you on the top wire? Okay, so it's dB dx, dFB dx, which means that by the fundamental theorem of calculus, right, which is just like the integration is the reverse of differentiation, you could reverse this by saying that FB is, you can integrate our force per unit length function, right, with respect to x, and then from 0 to L, the total length of the top wire. We have shown that in extension material, this is that function, okay? So the force per unit length decreases with x as shown, okay? Right, and so question B says that, right, so given a physical interpretation for the following, right, so I have this integral. So this integral is x times by our force per unit length density function, right? This is called a density function. So a density function is something that you integrate through like a dimension, or in this case, would be the length dimension, and then you get some physical property. So this will be like a force density, right? This is my density function, and I multiply my density function with x, which is our dimension unit, and I will integrate it throughout from 0 to L. Okay, so what is this doing? So if you think about this function right here, so this function right here times integrated with x is kind of like a force, right? So actually, so this function is it's like when I integrate this density function, so it's force per unit length. If I multiply this by x, it's kind of like a force, right? So this is kind of like a force, right? And then I multiply this by x, it's kind of like a force times by a distance. So what does that indicate? Right. So looking at this diagram here, like I have a force per unit length here, right? And I denote this by, and I multiply this point by x, so that this x is like the x value here, and so I multiply this by this distance, and then I have a force per unit length like maybe like this, I don't know, somehow. So that's kind of like creating a torque, isn't it? Right? It's just kind of like producing the torque, and then I sum it up from like 0 to L dx, right? That's kind of like calculating the total torque at each point, isn't it? Okay. So it's very constructively built up. This is actually calculating the total torque due to the difference in the force at each point, right? It's going to produce a torque. So actually, the top wire will actually rotate because this part experiences a larger force than this part. It's going to rotate this way, right? Because of that, right? And the torque for that rotation is evaluated using this integral. You can pretty much tell that from this symbol here. This is my tau, right? So look at the units for this. Because we're summing from 0 to L, this torque is associated to x equals to 0. Okay, so that's just me trying to explain it, right? So, and then moving on, we have part C. Part C asks you to, okay, now this is torque. Let's evaluate it. Let's try to calculate the total torque in terms of an equation. You need to solve the integral. Okay, so the torque is, if we put all the equations in, we put our f function in and we multiply this by x. Right, all the constants are out, and inside the integral, we just have x on the top and on the bottom, right? We just need to integrate this function. So this is a fraction function, right? In terms of numerator and denominator has a polynomial in terms of x to the power of 1. We could use partial fractions. You could notice that yourself, or we could try something different. We could try using this substitution right here, okay? Just some integration techniques, okay? If you try that, it becomes integral of 1 plus integral of something like 1 over x-ish, you get a log, right? Natural log. Yeah, so integration is just math. So this question is really a math problem. Yeah, so this, if you're confused with math, probably just don't do this question, okay? After you learn the math, this working out is pretty straightforward, okay? And then this really shows how, like, if you want to do actual theoretical physics, just a slightly bit of complication from HEC syllabus, you can see how physics uses math extraordinarily. Like it is so mathematically relied on math. Okay, so physics, do not afraid to use math in physics, no matter what. Okay. And I substitute the value, I think. There's a value given in the question. Yeah, set of values given. Okay, so this is it, okay? For this booklet, for this week. I'll see you next week. Enjoy physics.